The NPSM library implements a finite state machine framework for managing network protocol transitions. This document describes the core architecture, state definitions, transition rules, and event handling mechanisms. The system is designed to process protocol states in a deterministic manner with minimal computational overhead. All state transitions are logged internally for debugging purposes. The library maintains a single active state at any given time. State definitions are declared using the State Builder interface. Each state must have a unique identifier string and may contain entry and exit handlers. Entry handlers execute when a state becomes active. Exit handlers execute when a state transitions to another state. Handlers are optional and default to no-op implementations. The system does not enforce any particular ordering of handler execution. All handlers receive a context object containing transition metadata. Transitions are defined through the add transition method, which accepts a source state, event type, target state, and optional guard predicate. Guard predicates are Boolean functions evaluated during transition validation. If a guard returns false, the transition is rejected and the state machine remains in its current state. No exception is raised. The system records the rejection in its internal event log with a timestamp. Event injection is performed through the dispatch method. This method accepts an event identifier and an optional payload object. The method returns a result object indicating success or failure. If the current state has no transition defined for the given event, the dispatch call fails and the state remains unchanged. Event processing is synchronous and blocking. Multiple concurrent dispatch calls are serialized by the internal mutex. The state machine maintains an internal event queue for logging purposes. This queue stores all dispatch attempts, including rejected transitions. The queue has a configurable maximum size, defaulting to 10,000 entries. When the queue reaches capacity, the oldest entries are discarded. Queue inspection is performed through the getEventLog method, which returns events in chronological order without modification. Context objects are created automatically for each transition and contain the following fields: source state identifier, target state identifier, event payload, timestamp in microseconds since epoch, and transition duration in milliseconds. The context object is immutable after creation. Context objects are passed to entry handlers, exit handlers, and any registered transition callbacks. The payload field may be null. Callbacks are registered through the register callback method, which accepts a callback function and an optional state filter. If a state filter is provided, the callback fires only for transitions involving that state. If no filter is provided, the callback fires for all transitions. Multiple callbacks may be registered and are invoked in the order they were registered. Callbacks do not affect state machine behavior and cannot prevent transitions. The library provides several query methods for runtime inspection. The getCurrentState method returns the active state identifier. The getAvailableTransitions method returns a set of event identifiers that would succeed from the current state. The getTransition method accepts an event identifier and returns a Boolean indicating whether that transition is possible. These methods do not modify internal state. Guard predicates receive a guard context parameter containing the source state, target state, current event, and event payload. Guards may access the payload to make context-dependent decisions. Guards must complete within a configured timeout, defaulting to 100 milliseconds. If a guard exceeds the timeout, the transition is rejected and a warning is logged. Guard execution does not modify the state machine or any external state. Initialization is performed through the initialize method, which accepts an initial state identifier. If the initial state is not defined in the state machine, the method raises an illegal state exception. After initialization, the state machine is active and ready to receive dispatch calls. The initialize method may only be called once. Calling it multiple times raises an invalid operation exception. Error handling is performed through the result type, which encapsulates either a successful transition or an error code. Result objects are created through factory methods: result.success for successful transitions and result.failure for errors. The failure method accepts an error code enum and an optional message string. The getError method returns the error code if the result is a failure. No exceptions are thrown during normal operation. The library includes a configuration object for tuning system behavior. The config object accepts parameters for event queue size, guard timeout duration, callback execution mode, and logging verbosity. Configuration must be applied before initialization through the configure method. Configuration changes after initialization are not permitted. The The default configuration provides reasonable defaults for most use cases. Serialization is supported through the serialize and deserialize methods. The serialize method returns a JSON representation of the current state and event log. The deserialize method accepts a JSON string and reconstructs the state machine to that state. Serialization includes the current active state, all defined states and transitions, and the complete event log. Payloads are serialized as JSON objects and must be JSON compatible. Thread safety is ensured through internal mutex locking. All public methods acquire a read lock or write lock as appropriate. Read locks are held for query operations and write locks for state modifications. The locking strategy is non-locking, returning an error if a lock cannot be acquired within a configured timeout. Deadlock is not possible due to the single lock design. Concurrent access is serialized transparently. Performance characteristics are as follows. State transitions execute in constant time. Guard evaluation depends on guard implementation. Callback invocation is linear in callback count, and serialization time is linear in event log size. Memory consumption is proportional to the number of defined states and transitions. The event log may consume significant memory if queue size is large. Performance tuning guidelines are provided in the appendix. This concludes the core documentation for the NPSM library. Additional sections covering advanced topics, API reference, code examples, and troubleshooting are provided in subsequent volumes. The state machine framework is designed to be simple, predictable, and easy to reason about. Further questions should be directed to the technical support documentation or the inline code comments.